Then derivative of x with respect to t, took derivative of this and squared it, plus derivative of this and squared it, and then dt underneath the square root. Okay, that's our integral. How would we integrate this?
U sub.
Just a basic u sub.
Yes.
If we just, I don't need the squared here, right? Right there. If I just let this be u, right? The whole thing under here, u, the derivative of that is almost this. You're off by a constant. You should be able to get that with basic u sub. So I'm going to go dot, dot, dot on that one, okay? Because I trust everyone here can do that one. Let's go to the next curve. And this table has successfully completed the task.
Dun, dun, dun.
All right, so we'll go to this table next. We'll go clockwise. All right? So volunteers from this table to at least get me started here, because I don't even know what I'm supposed to do.
So I guess first the vector function.
Okay, so you want to be able to draw C2 then, right?
Correct.
So why don't I call it R sub 2 of t? See, we should have been doing this from the beginning. But y'all didn't seem too enthusiastic about it. Okay, go ahead. You want to draw that? Danny, you want to draw that?
I don't know if it's right.
Well, you know what? If you get it wrong, we're going to drop you from the class and you'll be asked to leave, right? Look, I want you to be wrong and I want you to be right. It doesn't matter. They're equally important. To be wrong and right is equally important in here. So go for it. What do you think?
No, my answer is for sure wrong.
Okay, so tell me what you're thinking.
Like, I was gonna say like it would just be t and then t, but that's wrong.
So you're trying to draw something here, right? This right here would best be described as a line segment, right?
Yes.
X equals
Right.
1.
Line segment? Okay, so can you draw a line with a vector function? What's the formula for a line? Is that couch potato one? U plus TV?
Yeah.
But we didn't use that. We used something else. Does that ring a bell? R of t, this is how we drew lines. It was R naught plus TV, right?
Correct. Yeah.
Okay, so R naught was always a starting point.
Yes.
So this is our starting point, right?
Correct.
And then V was our direction vector. So do you know the direction vector of that line? Yes? Okay, so I'm going to have you tell me, what is our starting point, Danny? 1,
Oh, yeah.
1, 1, right? Okay, plus, now T times V. What's this direction vector? What's the vector that connects from here to here? 0, 1? Yes? 0, 1. You could get that by just looking at these as 2 points, right? This is the point 1, 2. This is the point 1, 1. What's the vector connecting these two? You do 1 minus 1 is 0, 2 minus 1 is 1, so that's this vector, right?
Correct.
Now, that written, put this together now, right? Put them together and you would get what? 1
1 plus t.
1 plus t. Good. Now, what is our restriction on t going to be?
1 and then 2. Or 0, 1.
0 to 1. It will always be 0 to 1. Always. To draw a line segment. If you want to start at this point, end at that point, you should always use, it will always have 0 to 1. All right?
So we're getting, let's say we just put T on there.
Just t on what?
On the line.
Just t?
Yeah, and then we go from 1 to 2.
You could do that. You could. You would have to adjust your boundaries here on t. Yes. The way that I always, well, when we first started talking about lines, there was one part of one class where I showed you how to draw a line segment with a vector function. I said you always start with the first point, and then this direction vector will be the vector from the first point to the ending point. If you do it this way, your t will always go from 0 to 1, and you don't have to make any adjustments. It'll always work. Okay? So that's what I'm sticking with here. All right, so that's it. That's x of t, y of t. All right, so you're out, you're out, you're out. Two more.
B from 0 and 1.
What's that?
B from 0.
Okay, so integral. You want to do integral? Okay, integral 0 to 1. Okay, keep going. 2 times 2 times. Careful, hold on. Where are you? You just did integral. Let me put the formula up here. We're doing integral a to b, f of x of t, y of t, right? Square root of dx dt squared plus dy dt squared dt, right? Okay, so you got integral from 0 to 1. And 2, that's coming from there, right? 2 times x, what's x for you? 1, no, you're right. It's 1. It's just 1, good. Okay, over here it was what? It was t, right? But that was a different curve. Here it's 1. Okay, 1 square root of, all right, keep going, you're on a roll. 0 squared, so 0, it's gone, plus derivative of y with respect to t, which is 1, and then squared. So 1 squared is just 1. So dt. So that's just the integral from 0 to 1 of 2 dt, which we'll probably have to go to Wolfram alpha to get, right?
Yeah, basically,
Okay.
alpha alpha again, because there's
So that we could do with u sub, that we could do in our sleep, put them together, and that's your total area, all right? So what are you already feeling is the trickiest part of these so far?
just the calling out, you calling our names.
Me calling your name, yeah?
Yeah.
What? Yeah, finding the C. Probably getting the curve itself is, I mean, if you can't get the curve, you can't do anything else, right? All right, so let's look at the next one. It's not an example. Yeah, I'll leave that there. So the line integral that we just did is called the line integral along the path C, or along the curve C, with respect to arc length, right? Okay. But there are 2 other line integrals that we could calculate, which are, man, I thought I had an animation for this. Oh, I do. I have it below. I did it. I added that to the notes. I forgot. The line integral, so we have the line integral with respect to arc length, right? But we have these other 2. The line integral along C with respect to x, and the line integral with respect to C, a line integral along C with respect to y. And so look at the change in the formulas. Same, different, right? So this part right here, x prime of t, I want you to see what that is. What it's doing is it's taking this formula dx dt squared plus dy dt squared dt, and it's zeroing that out. Okay? It's saying that the derivative of y with respect to t is 0. And if that's 0, that's just the square root of the derivative of x with respect to t squared, right? Which is just derivative of x with respect to t, which is basically this, right? So if I'm saying that the derivative of y with respect to t is 0, that means that the y is being held constant. So visually what's happening is this. What we're doing is we're looking at that curtain. Where's my curtain? No, it's there. But y'all see, what we had done is tried to draw this curtain, right? Imagine we're looking at it from the side, like this. Where's my damn curtain? Oh, here's the curtain. Okay, there's the curtain. There it is. So there's the green is the curtain we were looking for the area of, right? Imagine projecting that shadow onto the XZ plane. So it's kind of like we're coming in from this side, and we're projecting its shadow onto the XZ plane. That shadow would have a different area than our curtain did, wouldn't it?
Yes.
That's what the line integral with respect to x is. It's that shadow. Now, what do you think with respect to y is? It's the shadow on the other wall, okay? It's that area. All right, that's what they are visually. So later on, as we move through this section, you're going to see these two integrals come up quite a bit. This line integral of some vector function. We're using p here instead of f, but this is some surface with respect to x, okay, this line integral, plus some other surface with respect to y. We're going to see these a lot being added together. So this notation is a notation we will use. All right, so we put them together. This is just this right here means this. All right? So I say that up here. They're going to appear a lot together, so just get used to that notation. And I believe we have an example now. All right, here we go. You ready? Your last one, right?
Solve the entire problem.
All right, here we go. I'll help you out since this is our first one. It's asking us for the line integral along the curve C of sine x with respect to x plus the line integral along C of cosine y with respect to y, where C is the top half of the unit circle, right? From 1, 0 to negative 1, 0, and the line segment from negative 1, 0 to negative 2, 3. So how about you help me? I'll draw it first, and then we can go from there. You can help me get the... So the first part, I think, pretty self-explanatory because we've done that already. We're going to go from the point 0, 0, and that's not 0, 0. That's the point 1, 0 to negative 1, 0, right? And then from there, we're going where? Negative 2, 3. So that's going to be like out here, negative 2, then up 3. That. So there's our C2, and there's our C1. So I know you're capable of this, so I'm going to ask you for C1, okay? For C1, what's the vector function that will draw me C1? Cosine t, sine t. Restrictions on t? Okay, 0 to pi. Perfect. All right. Everyone agree? Yeah. Okay, that we've done. Now let's see if anything that we just did on the last problem connects. Let's take care of C2, which is my second curve. So that second curve is a line segment, right? It's a line segment, straight line. So I would recommend you use this, and I'll let you take it from here. So R naught, negative 1, 0, plus t times direction vector, but this vector needs to be the vector connecting those 2 points. Subtract. This one, I'll put it up here for reference for you, 2, 3, and you're going from here to here.
So
Negative 3, negative 3. What do y'all think? Or the other way around? Or is it? You're doing negative 2 taking away negative 1. So negative 1. And then your second one is just 3. Okay, now let's put them together. That looks like a 6, sorry. So this put together is... Do you want to finish it? I mean, you're there. You're pretty much there. Minus t, and then 3t. Okay, there we go. Oh, t, sorry. What's the restriction on t? Always going to be 0 to 1, as long as you do it the way that I just showed you to do it. You always start with your initial point being here, And this vector is the vector connecting the two. If you do it that way, every single time it'll go from 0 to 1. Okay? All right. We happy?
Yeah. Even if it's like just looking at it, you would think it's like from that point to that point, not the domain, but.
Wait, why is it from 0 to 1 always?
Because it works. I mean, look, plug in 0. Plug in 0, and where are you going to be? Plug 0 in here for t. Where are you?
Negative 1.
-1.
Oh, yeah. Sorry.
-1, 0, right? Okay. Now plug in 1. Where are you?
Oh my gosh, I'm an idiot.
-2,
and 3.
3, right? Which puts you here. And so somehow you've got from here to here, right? And from t being 0 was here and t being 1 was here. And that means everything in between, you're going to go from here straight to here.
Yeah.
Is that enough? I mean, it's the way you do it initially. If you do it the way I've shown you, which is starting point is always this vector. The vector going from here to here is this vector, then it'll always be 0 to 1. There are ways to do it where you can do it different, okay? There are ways, but to me that's always seemed like the easiest, most straightforward way of doing it. Plus 0 to 1, I like integrating from 0 to 1, you know? All right, we're moving on. Making our way around the back corner of the room here. So what am I going to do now? Because I really kind of am lost. Okay, so we've got to do this integral for both, right? But this integral is actually two separate integrals. Okay, so let's set up that first one. What would you like me to write here? You want me to split it? I'll just like write it twice. So I've got to do the integral over C1, right? Because I'm working with C1 here. Sine x dx, and then plus the integral over C1 of cosine y dy, right? Okay, you want to keep going? So we're in C1 here. What are we doing? So for x, we're going to replace it with cosine of t. That's weird, but that's what we do. Okay, so this is going to be sine of cosine of t. And then what do we replace dx with? Yeah, the derivative of this, which is negative sine of t. Yes? And my integral is going to go from 0 to pi. Okay, so this first one is, I'm going to do it up here. Integral from 0 to pi of sine of cosine of t, but then times, you said the derivative of this. Why am I not doing the square root? Yeah, because this is not with respect to arc length. This is with respect to x. So the formula changes, and all you do is take derivative of that one and don't even worry about that one. So this is negative sine t dt, right? That's the first one. I think I can get rid of all this, move out of the way. Could we handle this? If you had to integrate that? Basic u sub. U is cosine t. There's its derivative. This should work out real nice, because it'll turn out being like sine u, and the antiderivative of sine u is negative cosine u. That should work out real nice. But then I have this one, right? So you want to keep going? Okay, plus, we're still working in C1. Integral, 0 pi, then cosine of sine of t. Okay, that's this part, and then dy times cosine of t dt. And that one we could also do with u substitution, right?
Yes.
Okay, so that would take care of the line integral along C1. Now it's time to move on to C2. So we'll add to this, now us moving along C2. So this was along C1, and these next two are going to be along C2, right? So for this one, this will be along C2. All right, where are we at? You ready? Okay, so we're now working in C2. And we're doing the same thing, right? Hold on, let me get it written down. Okay, that's it right there. That's what we need to do, right? This same thing along C2. So go ahead. This first one?
It is sine of -1 minus t
Okay. Sine of -1 minus t.
times -1.
Yep, times derivative of that with respect to t, which is -1, and then dt, right? One thing missing there. Your limits of integration,
Oh, yeah. 0.
right? 0 to 1, right? 0 to 1. Okay, so 0 to 1. And then plus
Plus the cosine of 3t.
cosine, now you're using y, so 3t. 0 to 1, yep.
Cosine of 3t times 3.
Times 3 dt. Done. And those integrals should be pretty straightforward, I think. Would you agree? Okay.
They're not gonna be pretty, but
Yeah. All right, so I'll stop here. You would just crank out each of those now. You get numerical answers for each one, right? All right. Not so bad, is it? No? Yes? No? What do y'all think? Yeah. All right. Switching gears a little bit. All right, now that we've done a few examples and you kind of get a flavor for what's happening, some questions about our path. What happens if we change the direction of our path? So, you know, we could go both directions. We have 2 points, right? We could go from A to B, or we could go backwards and go from B to A. In the case that we are going from A to B, if we call this the path C, then negative C is the path going the other direction. Okay, so that's just notation. If you see negative C, it's the path in the opposite direction. But what happens when we go backwards? Do you think that finding the area under the curtain matters if we go two different directions?
yes.
You do?
I think it's just gonna change. Oh wait, no, area under the curtain. No, it doesn't matter then.
Yeah, it may not, right? So let's take a look at what happens when we change the path. So if we calculate the line integral along C of some surface with respect to, let's start with this one on the bottom. With respect to arc length, that's the area hanging from the curtain, right? And it doesn't matter which way we go. We can go along the curve one direction or an opposite, and we're going to get the same answer either way. And the reason why is because ds is an arc length. It's the square root of the derivatives squared and added together, right? So if you change your direction, that arc length doesn't change. However, if you integrate and you do it with respect to x, that's like back in Cal 2. Remember I said it was the shadow on the plane? Yeah. Okay, so when we do the integral from A to B, that's like from left to right in Cal 2, we get one answer, right? We get one area. But if we switch the integral and we go from B to A, instead of from A to B, we switch it, it gave us the same answer but opposite sign. And it's because our dx, the width of our rectangle, when we go backwards, when we do the subtraction, we get a negative number down there. So because you get a negative, it counts that as a negative area. So same thing happens with the line integrals. When you do it with respect to x or y, changing the direction of the path changes the sign of the answer. But if it's with respect to arc length, we have no worries about changing the direction, all right? So that's just a result we should just be familiar with as we move ahead. There will be a couple of problems later on where we change directions and we need to know what happens. All right, now here's a more profound question. Path independence. Let's say we have 2 points, A and B, and we connect them with two different paths. So if I want to go from A to B, I could go straight line segment, right? That's one way I could go. I'll call that C tilde. And then another path that curves around and comes back. Do you think that the line integral along those two curves will give you the same answer? What do you think? In general, do you think that the line integral along these two curves will give you the same result? No? Yeah, probably not, right? Probably not, because it's like the area hanging from the curtain, right? Should be different on those two curves.
Yeah.
Like the curtain above this curve is different than the curtain above this curve. Agreed? So, I don't know, maybe, like in general, yeah, it doesn't seem like it could be true, but let's check. Let's just do an example. One of the great things in mathematics is that if you believe something's true, one way to figure out whether or not it's true or not is just try and find one example of where it's not true. So look at this right here. We have this, this line integral we're trying to do. All right, we're going to look at this along two different paths. First, the arc of a parabola, and then a line segment. So both of these. So these are two different problems that we have to do. I'm going to call this path C and this path C tilde. So let's come up with the paths first. We'll split the board in half, and let's do C first. Where are we at? Who's up? Who's up? You're up. For C, arc of that parabola. All right? I'm going to draw it first, and then you'll help me try and come up with the curve, the vector function. So this parabola opens which way? So to the left, like this, okay? And it goes from the point -5, -3, -5, -1, 2, 3 here, to 0, 2, like that, right there, okay? And opens up sideways. It actually comes up to, we know it goes up to 4 because this 4 right here. So this is like a parabola, opens down, and this is your height 4, but it's turned sideways. So we good with that? Okay. I'm going to call this R subscript C because that's C, and I didn't use C1 and C2. I used C and C tilde, so I'm going to put C here. Any idea? Start what point? What?
From 4.
From
Are you
4?
trying to find the x?
I'm trying to come up with the parametric representation of that curve. So it's a curve now. It's not a straight line. So that's going to be a little harder. So let me ask you this. What if this right here said y equals 4 minus x squared? That'd be like your standard. And I told you if it was this, then what would you put here? What do we put here? If it's like a standard function, you always put t here, and then over here would be that function with x replaced with t. So that would be 4 minus t squared. Okay, that's what would happen if it was that. But it's reversed, right? So how do you think that changes this then? Yep, 4 minus t squared here, and this time t for the y. Okay, everyone? If it's solved for x instead of y, then you do it backwards here. Now, kind of a big deal now. What is our restriction on t? So I'll help you out. T controls the y, right, which is up and down. Can you tell from here what our up and down restrictions are going to be? negative 3 to positive 2. So this will go from negative 3 to positive 2. Do y'all believe this works? Negative 3, let's just try it. Negative 3 right here. 4 minus negative 3 squared is 9. 4 minus 9 is negative 5. Negative 5, and I plugged in negative 3. So if I start this out, I'm going to be at negative 5, negative 3, right there. Now, it's a parabola, so it's going to start drawing a parabola. But when I get to 2, I should be at 2 minus 2 squared, 0, 2, which is right there. So it should draw me everything in between there. All right, good. All right, let's get the other curve right now. Let's get C tilde. You ready to move on? We ready to move on? You ready? Whoever wants it over there.
Should be obviously from the point, but you can just do the vector function, -5, -3,
Okay.
plus t, 5,
5, 5. Okay, so this, because it's a line segment, like those are, we now like line segments, don't we? Because they're easy to parameterize, to find the parametrics for. So I'll call it R sub C tilde of t is those two put together. So -5 plus 5t, and then -3 plus 5t. Restrictions on t? 0 to 1, right? Line segment? Does everyone agree with this? Any questions? All right. Now we've got to do the integrals, all right? So let's do this one. We're going to set it all up, get it all ready, and then we're going to set that one up, get it all ready, and then we're going to take a break, and during the break I'm going to get on Wolfram Alpha and calculate them, and we'll see if they're the same or not, all right? So who's up? You ready? Okay. Let's do this one, and we want to set the integral up for this. There's your integral, right? All right, so go ahead, lead the way.
So it's going from -3 to 2.
-3 to 2, I'm going to give myself some room here. Okay, integral from -3 to 2, okay? T squared, so we're replacing the y with this because this is y. So t squared, keep going. -2t because we're doing this with respect to x, so we're taking derivative of this piece. -2t.
Plus 4 minus t squared.
dt, hold on. Right. Okay, so that's our first integral, right? Now we're going to do this piece right here, which I'm going to do as a separate integral, even though you could just do it all together. I'm going to just do it as a separate one. Okay, now
That would be 4 minus t squared.
4 minus t squared, that's x. And then dy, which is derivative of this with respect to t, which is 1 dt. Okay, good. Keep going, you're rolling, you're cranking. Plus, oh wait, no, sorry, this is two different paths. We'll figure that out. Now, compare that to this one.
So that's 0 to 1.
0 to 1.
Okay.
Yeah.
-3 plus 5t all squared.
Yep, -3 plus 5t, that entire quantity squared,
Times 5.
times 5, that's dx. And then you want to do this one all together? We can do this one all together, just so you can see the two differences. Plus, now you're going to do x dy, right? So x would be times dy, 5, and then this one dt still, right? So that's that whole thing dt. There we go. Questions? So the ultimate question on this problem is, do these two curves that connect the same 2 points, give you the same result, right? We don't know yet. We'll take our break. It's 3:47. What do you say we come back at 4? Yes? Okay, we'll come back at 4. Please remind me to start the camera back up at 4 o'clock, all right, because I'm going to turn it off.